Hello there. We're about to take a look at something really interesting today, a kind of hidden language. Think of it like an architectural blueprint that lives behind almost every single piece of software you've ever used. It's the secret to how computers actually understand our code.
So, have you ever stumbled across a line of symbols that looks something like this? I mean, it kind of looks like abstract math or maybe just some random cryptic message. What's the deal with it?
Well, it turns out this isn't just some abstract puzzle. This is actually a rule. It's a fundamental piece of that secret language we use to tell computers not just what to do, but how to understand our instructions in the first place. So let's dive in.
To really get this, we have to start with a pretty basic problem. How does a computer, a machine that just sees a bunch of characters on a screen, figure out the actual meaning and the structure that's hidden inside them?
Just look at this simple math expression. Now, for you and me, it's totally obvious, right? We know what to do first. But for a computer, this is just a meaningless line of text. An open parenthesis, a 3, a 4, a dash, another 3, a close parenthesis, a star, a 4, a 2. It has no built-in idea that you're supposed to subtract first and then multiply. So to figure all that out, the computer needs a guide. It needs a formal set of rules, a blueprint, that spells out exactly what a valid piece of code is even allowed to look like. And that blueprint, well, that's what we call a grammar.
Okay, so let's spend a little time with this whole blueprint idea. In the world of computer science, what is a grammar really, and what does it actually do for us?
You know, this quote really just sums it all up perfectly. A grammar's whole job is to define the syntax, the structure of a language, with absolute, pinpoint precision, but in a way that we humans can still read and make sense of. And yeah, that blueprint analogy, it's just so fitting. An architect's plan shows you exactly how the walls and the doors and windows all fit together to form a solid house. A grammar does the exact same thing, but it shows how numbers and operators and keywords all fit together to form a valid program. All right, so if the grammar is the blueprint, what are its building blocks? Let's break down these rules of construction and see what these plans are actually made of. Let's go back to that strange rule from the very beginning. This one little line is a perfect example of what we call a production rule. It's a rule that defines what an expression is allowed to be. We're going to take it apart, piece by piece. Okay, first up, we have things called non-terminals. These are the big abstract ideas. In our blueprint analogy, these are like the names for the different spaces in the house. Living room, kitchen. They aren't physical things, they're concepts. Here, exp is our non-terminal, and it just represents the general idea of an expression. And then we have the terminals. These are the total opposite. They are not abstract at all. They're the literal, physical things that you actually type in your code. They're the bricks and the wood of our blueprint, the actual plus signs, the parentheses, or maybe the concept of a number. So a grammar rule or a production is really just a simple instruction. It shows you how you can build one of your abstract concepts, one of your rooms, out of the concrete materials, the bricks, and maybe some other smaller rooms. Let's make this feel a little more real. How does a computer take these simple rules and use them to understand the structure of the code we saw earlier, the one that represents 34 minus 3 times 42? Well, it happens through this really neat process called a derivation. It starts with the biggest, most abstract idea it has, the concept of an expression. And then, one step at a time, it uses the rules to expand it. It's like unpacking a nested box. The rule says an x can become x op x. Great. Then it can take one of those expressions and turn it into alt x. And it just keeps going over and over, replacing the abstract parts with more concrete ones until there's nothing abstract left, just the actual symbols from our code. And what you're left with after all that unpacking is this beautiful structure. It's called a parse tree. And this tree is the final blueprint. It's the computer's complete, structured, totally unambiguous understanding of how our little line of code is put together. Now here's the thing. Creating one of these blueprints, it's a really delicate process. What happens if the rules aren't written so clearly? What if they can be interpreted in more than one way? This is a huge problem known as ambiguity. It's what happens when a single piece of code can generate two or even more completely different but equally valid parse trees. And for a computer that needs absolute certainty, that's a deal breaker. A classic example of this is something called the dangling-else. So look here. Based on one very common way of writing the rules for an if-else statement, this single piece of code can create two different structures. In one tree, the else statement belongs to the inner if, but in the other tree, it attaches to the outer if.
The code hasn't changed at all, but the meaning is completely different depending on which tree you pick. Both are technically allowed by the rules, but they lead to totally different outcomes. So, which one is right? The computer has no idea which one the programmer actually intended.
And that's exactly why designing a language grammar is so critical. The whole goal, the gold standard, is to write a grammar that is completely unambiguous, a perfect blueprint that gives you one, and only one, correct and predictable structure for any valid piece of code you could possibly write.
So, after all of that, what's the big takeaway here? We've seen how just a handful of simple rules can work together to build something with really deep and powerful structure.
You really don't have to memorize how to write a grammar. But maybe the next time you write a line of code and the computer just gets it, you can take a quiet moment to just appreciate that invisible blueprint, that elegant grammar working silently in the background to make it all possible.
You know, this idea of a hidden formal structure isn't just for programming languages. And it kind of leaves you with a final thought to ponder. What other invisible rules and blueprints are out there quietly shaping the technology and the digital world that we navigate every single day?